So what is exactly the delta method, and how it is approximation to the functional form of your asymptotically any distribution you can assume. Maybe you can assume the functional form of normal distribution. You can assume functional form of your sample mean, sample variance. Okay. So what is exactly the delta method? And usually we'll do it for the univariate. Okay. So let's take down this first. So what is the basic understanding about the delta method? So asymptotic distribution for a function of an asymptotically normally distributed, typically it's considered for normal random variable. Okay, normal random variable. So there is a theorem based on that. So we'll just state the theorem. We don't have the proof of this. Okay, we will just require the theorem, understanding of theorem, what it is and how it is exactly work. Okay, so let xn be a sequence of random variables such that root of n xn minus theta converges to normal distribution, converges to normal random variable, normal distribution in distribution with 0, sigma square. We can assume this is maybe the function of your random variable x. So xn converges to x, where theta, sigma square are finite constants, then root of n functional form of your xn minus function form of your theta. This is converges in distribution with normal with 0, sigma square into first derivative of your functional form of theta, where the first derivative exists and it is non-zero. Okay, so this is the basic definition of your delta method. So whenever we apply any delta method, we should know this theorem. What does the theorem says? If you have any sequence xn of a random variable such that, this is the by central limit theorem, one can say that this particular sequence converges in distribution with mean 0 and variance sigma square. It is something like your xn is converges to x. Okay, where theta and sigma, this theta and sigma are both are the finite constant. Then what the delta method says, if I'm assuming any function of my xn here, which is your f of xn, or any function of my theta, which is f of theta, this is also converges in this distribution with mean 0 and variance sigma square into your first derivative of this function form of theta. Okay, so this much extra we have to attach to according to the delta method. Let's take one example here. Suppose the distribution of x follows binomial 1, for example. Okay, then you know very well what would be the mean of this, what would be the variance of this. So mean will be p variance will be P1 minus P. Okay? Here, if we assume let x, let us assume the function form of x here. So let us say the function form of my x is x1 minus x. Okay. So what is the first derivative of this? It's 1 minus 2x. Correct? So according to central limit theorem, root n x bar minus p divided by root of p 1 minus p. It's something like your mean minus your parameter divided by your variance. This is follows normal with 0, 1, right? So if we assume the functional form of this x, so what would be? It is going to be root of n functional form of your x bar minus functional form of your p whole thing divided by root of p 1 minus p into your derivative of first p. This is again follows normal with 0, 1. Okay. So if one may interested to get the probability of your x bar minus 1 minus x bar lesser than some quantity, can assume some quantity. This can be obtained by just because this we have converted by central limit theorem, it is normally distributed. So one can take the simply it is the functional form. You can take just a probability, or you can take the CDF of that, which is going to be it's root 10 into t minus p1 minus p whole thing divided by p1 minus p into mod of 1 minus 2p. Now why we consider mod here? Because if this p will be lesser than greater than half, then this quantity become negative. Okay, so if you did take the mod of this, it's become positive and one can get this distribution very easily. So this is just an approximation part. Okay, this is just an approximation part using the delta method. You can just go through this concept whether it is clear or not. Okay, then we go ahead. Any query here?
Sir, f of x bar becomes t, right?
Sorry?
Sir, f of x bar becomes t, right?
F of x bar become
T.
t distribution of saying what? I didn't get it.
Sir, in next step, it is assumed that f of x bar equal to t, right? Yeah, in this step.
No. See, this is the function of your distribution of sample mean. Here we have assumed this is the function x1 minus x is my function, but my interest is for the function of my asymptotically normally random variable, means I am using for the mean. So if it is x bar 1 minus x bar less than equal to t, if you are interested for like it's something like CDF, then how you can get that particular value? तो CDF आपने निकालते हैं तो कैसे निकालते हैं? You remember, if you have any random variable x is less than equal to a, तो कैसे CDF निकालते हैं आप? How do you get this? It is nothing but what? It's simply your probability of your z will be less than equal to a minus your mean upon sigma square, na? How you calculate this? So this is not, so this is not equal to t. This is nothing but a particular value. So it's this minus mean upon sigma. So it's become your phi of a minus mu upon sigma. Remember just standard normal distribution. Is this clear?
Yes, sir.
Okay. Anybody else? Anybody else? Are you getting this, all students? It's a little different method, delta method. So only the concept is here, whenever you are obtaining the variance, usual central limit theorem, we take directly variance. But now using the delta method, we need to be take the variance into multiplied with the functional form of first derivative of the functional form of your theta and square that. Okay, so that much difference is there in the basically a delta method. Okay, so let's go ahead. So let us consider how one can able to use R to approximate the distribution of functional form of sample mean. Okay, so let us consider using R and the delta method to approximate the distribution of function of the sample mean. Okay, so we'll consider a delta method to get the function of my sample mean. So I may consider the function maybe sample mean. I will consider the function maybe the square root of my sample mean, distribution of my x bar square, or maybe other distribution. So how one can get the distribution? So sometime maybe in the CSR or net offset, or maybe in other paper, maybe you have studied in the probability distribution. They usually they ask what is the distribution of, if x follows this, then what will distribution of x bar square, x bar cube. Okay, so one can use the delta method and one can get the distribution of this. So, but that is by using the distribution of using the delta method. Okay, one can have another method also, but specifically we are focused on the delta method. Okay, so let us consider here again. Let's say let xi be IID with f distribution assume expected value of xi is equal to mu, and instead of writing the variance, we can use VAR. Variance of xi is equal to sigma square. Let x bar is equal to 1 upon n summation of xi. So the first one, by CLT, we know that root of n x bar minus mean, this is converges in distribution with 0 comma sigma square, and for a given n, the distribution of x bar follows normal with mu comma sigma square by n. This result you are knowing very well, because of by central limit theorem, distribution of your x bar is this, right? It is very simple. If let's consider second one, find approximate distribution of your root of x bar. Okay. So x bar is very easy. One can get the approximate distribution of x bar is this well known result, right? Studying from F5BSc. Okay. So if the distribution of x is normal, then one can have the distribution of x bar by using the central limit theorem. The distribution of your sample mean follows normal with mean sigma square by n. But what would be approximate distribution of root of your x bars? Root of your x bar. So x bar, you know, we need to be get the root of this x bar. So how we can get this x bar? So let's define this function f. So f become, let f of x become, let f of x become root of x, for example. Okay, so I'm just considering the function of this. So f of x become this. So one can get second derivative of, sorry, first derivative. So what would the first derivative here? It's 1 upon 2 root x. Correct? It's 1 upon 2 root x. So now, applying this concept again, root n root of x bar minus root of your mean, this will be approximated to normal with 0 comma sigma square, and you have to multiply the functional form of my mu. Remember, it's a functional form of your f dash mu square. So f dash mu क्या होगा आपका यहाँ पे? What would be your f dash mu? It's 2 times root of mu, right? So it's going to be how much? How it is?
1 by 2 root mu.
Square. Nah? It's just look at this function. It's 1 upon, it is that first derivative square. The first derivative is 1 upon 4 root of this. So this is 1 upon 4 mu. So it's going to be 4 mu. Just check it.
Yes.
Yes, got it, everybody. Okay, we can take mu here. So you will get 1 upon 4 mu. So what will be, because I am interested to get the distribution of this, but I know root of and root of x bar minus root of mu, it follows mean with 0 and sigma square upon 4 mu is your variance. So for any given n, the distribution of root of x following normal with mean mu, root mu, comma, sigma square upon 4 n mu. Check it. Let me know if we have any query here, students. Can you find the third part here, which is find approximate distribution of x bar square here. Just try for this. N, what would be it is? So here we're considering the function is x square. So the first derivative one can get here 2x. So the distribution of x bar square will following having this just a second, this you can take with distribution, having the distribution with this. Similarly, having the distribution converges in distribution normal with mean 0 and variance sigma square into the first derivative of function at mu. So it's going to be 4 mu square sigma square. So for any given n, we can consider the distribution of x bar square, which is follows normal with mu square, comma 4 n square sigma square upon n. So it is mu square. This is mu. So this will be the following your third distribution. Now let us take little complicated distribution. For example, you're interested find approximate distribution of, let's say, root n x bar minus mu plus x bar square. So here if you just observe here, you have already obtained the root n x bar minus mu distribution, right, which is this here, right, and you have obtained the distribution of x bar square. So you can add up. No, it is not like that, because they are not independent event. Okay, because there's nothing condition is given whether they are independent or they are dependent. Okay, so we cannot consider directly this, and we can say that by you can say uniqueness property of normal, we cannot say the mean will be added and variance will be added like that. Okay, so this result is fair. So again here we have to define the function form, and that function form is a little a different way. So let's say my function form of x is, it is x plus x square upon root n. Suppose this is my function form. Okay, from here you can take x, and from here distribution of x square, but here I'm taking x square upon root n, because if you just observe x square you have considered simply x bar square, you have considered x square. Okay, but here now I'm considering x bar square upon root n. So this is the way to consider, and just try to get the distribution of this function. So let's take the derivative of this first. So x is going to be with respect to x, so it is 1 upon 2x upon root n. Okay, so one can get the approximate distribution, which is root of n. It is a root of n into, because if you're considering here x minus mean, okay, so it is going to be x minus mean plus x bar square upon n minus mu square upon root n. So this would having the distribution with mean 0, 1 upon 1 plus root of n mu square into sigma square. So this will be the distribution of under this condition. Just check whether how it is. So exactly same way I did it for x bar. So x bar minus mean, and similarly for x bar square root n minus mu square upon root n. So that will be converges to in distribution with mean 0 and sigma square upon multiplied with this particular quantity. So one can have the distribution of then original one, which is the root of n x bar minus mu plus x bar square. This will follows normal with mean mu square upon into 1 plus 2 of root n mu square into 6. So this is the distribution of x bar minus root of x bar minus mu plus x bar square.